Okay, so in today's video we want to look at horizontal translations of our graphs of sine and cosine. So in the previous video we introduced the graph shapes y equals sine x and y equals cosine x. We talked about period and amplitude being features of those graphs, and then looked at how to change the period and amplitude through dilation of the functions, and also by also I mean not change the period and amplitude, but we also looked at making reflections of the sine and cos curves. So we're familiar with those. So what we want to now do is add in the horizontal translation. So hopefully we recall that when dealing with functions, if f of x becomes f of x minus b, it has translated to the right by b. Okay, providing that b is a positive number, obviously. If b was a negative number, then obviously we've got x minus a number, and it's x plus a number, and it's gone to the left. So thinking about therefore y equals sine of x plus b, if b is bigger than 0, that is to the left by b. Cosine of x plus b is taking the cos graph and moving it to the left by b. Sine and cosine of x minus b, taking those graphs and translating to the right by b. Before we fill in any more, let's just have a quick reminder of that visually. So here is our graph of y equals a times sine of n. Actually, let me just go back, sorry, to the notes, and let's just first of all note that individual effect of b, which is to translate the effect of b is, I should really say to translate, just as a complete sentence. The effect of b is to translate the graph left or right. Okay, so for example, if we had y equals sine of x plus pi, that means we've gone to the left by pi. If we have y equals sine, let's do cosine just to mix it up, cosine of x minus pi on 3, this means we've gone to the right by pi on 3 units. Okay. Alright, so let's summarize that in here. So we want to now combine that together with our dilations and reflections. So we've already looked at y equals a times sine of nx, y equals a times cosine of nx. So we want to make sure that it's much easier to sketch the graph if we first of all dilate the graph, so change the period and amplitude, and then we worry about translating it. And so in order to get that order correct in the transformations, the function must be written in this form. Okay, so the important thing is here is that the n, the period change, the dilation from the y-axis, must be factored out. So not outside of the sine, it's still going to be inside the sine function, but it must be factored out in order to correctly identify the horizontal translation. Alright, so for example, if we had, actually let me just fill in this first. So we know with these two functions, we already know our a value. The sine or cos graph has an amplitude of a, and remember we put in these modulus of a, or absolute value of a, meaning it's the positive value, regardless of whether a is positive or negative. So if a was negative 2, the amplitude is positive 2. If a was positive 2, the amplitude is still positive 2. If a is negative, the graph is reflected in the x-axis. Changing n, the sine or cos graph has a period of 2 pi over n. Again, it's the absolute value of n, the positive value of n. But if n is, sorry, that should say negative, if n is less than 0, then the graph is reflected in the y-axis. We won't really see this happen very much because we can reflect if we reflect the sine graph in the y-axis, it's the same as reflecting in the x-axis. If we reflect the cos graph in the y-axis, it just produces the cos graph. So we don't really need to worry about n being negative very often. Okay, b, the sine or cos graph is translated left or right by b units. Sorry. So in terms of identifying the left or right, I would refer to this example I've given up here. So adding a number moves to the left by that many units, subtracting a number moves to the right by this many units. So as I said, coming back to that, the idea that the n value needs to be factored out if you're going to correctly identify the horizontal translation. So for example, if we had y equals sine of 2x plus pi, we would need to first of all factor the 2 out inside here, and this becomes x plus pi on 2 to be able to see dilation by a factor of half from the y-axis, so the period is halved, period becomes pi, and then to the left by pi on 2, not to the left by pi. Okay. In this format, it's technically going to the left by pi first and then dilating, so then you're changing the period. That's a much more difficult thing to do when you're sketching the graph, so it's always best to write it in that standard form first. Before we move on to the examples, just to verify or demonstrate what we're talking about there, and actually to just make one clear point about horizontal translations. So here we've got our graph of y equals a times sine of n times x minus b. So here I can adjust the n value, which is to change the period. I can also adjust the a value, which is to change the amplitude. But what I want to focus on here is adjusting the b value. Now I've set the step size, and unfortunately it's now displayed as a decimal here. So the step size meaning every time I press this little arrow, b is going to increase by that amount. That's actually pi on 12. Okay, it's exactly pi on 12. It's more precise than what we can see there, and that's just going to make this translation fit with my scale a bit better. So if we're translating, so if I press up once, that's the graph has moved to the right by pi on 12, because it's now the rule is now y equals, now a and n are both 1, so the rule is now y equals sine of x minus pi on 12. So we've gone to the right by pi on 12. X minus 2 pi on 12, which is minus 6 pi. 3 pi on 12, 4 pi on 12, 5 pi on 12, etc. Now, one thing I want you to notice of what can happen with our sine graph is if we translate far enough, so if I were to actually translate to the right by 2 pi, I've translated the graph by a whole period. And so actually I'm just back to exactly the same graph that I had at the beginning. So in terms of translation, you can often describe the same graph using a number of different translations, because if you want to translate to the right by pi on 3 and the period of the graph is pi, for example, if you were to translate to the graph to the right by pi plus pi on 3, which is a whole period plus pi on 3, that's the same as translating to the right by pi on 3. Okay, so we can see, there'll be a certain point where, okay, at this point, right now, the b value is actually 2 pi. So that is the sine graph translated to the right by 2 pi. So once again, the drawing on this is pretty poor, but what's actually happened is the point that was here at 0 has now gone to the right by 2 pi. It's actually now technically there. But it doesn't really matter because it's a periodic graph. If we translate to the left or right by a whole period, we're just going to get exactly the same graph. Okay, let's go back and draw some examples in the notes. So I think there's 3 examples we're going to work through here. So we want to sketch the graph of 3 times sine of x plus pi on 3. Okay, so if you remember previously, we want to think first of all about what shape are we dealing with here. It's a sine graph with no reflection, so it's going to go up first and then down. We can see that the amplitude has changed here because of the dilation by 3 from the x-axis, so the amplitude has become 3. We can see there's no n value here, okay, so there hasn't been a period change, so that means, or n is 1, I guess, so the period remains at 2 pi. There's been no dilation from the y-axis. And then we've also got this plus pi on 3 in here, so our graph has translated to the right, plus means to the left by pi on 3 units. Okay, now you'll remember in the previous video we talked about thinking about scaling our x-axis. This is really important for accuracy of your graph. And in order to scale our x-axis, we want to think about the period divided by 4. Because remember, that's going to enable us to mark the 5 key points that define the period if we split the scale of the period by 4. So in this case, that's going to mean we want to at least have a scale of pi on 2 to be able to get the shape of the graph right. However, now that we're also going to be translating horizontally, if we want to move our graph to the left by pi on 3, we're also going to need our scale to involve units of pi on 3. Okay? And so what I want to think about is if I need to be able to mark units of pi on 2 and units of pi on 3, I'm going to need to use units of pi on 6 to be able to do that. Okay, because 3 pi on 6 is pi on 2. So if I use pi on 6s, I'll be able to mark in in units of pi on 2. Equally, 2 pi on 6 is pi on 3. So I'll also be able to work in units of pi on 3. Okay, so it's really important that you combine these two things together, your period and your horizontal translation, to think about what scale is going to be helpful. Okay, and once again, time invested at the beginning here saves time later on. Okay, we want to draw our graph from 0 to 2 pi. So I'm going to think about that, but I am going to leave a bit of room to the left of the y-axis just so I can think through that translation to the left by pi on 3. So 0 to 2 pi, we're going to see one complete period of the graph, but it's not going to start in its usual place because of the translation to the left, but we're still only going to see one full period. Okay, so let's think about what's happening here. So we've got 2 pi. I'm going to split that in half, that's going to be pi. And split that in half again, that's pi on 2. But then I'm going to divide each of those, sorry, not 3 pi on 3, 3 pi on 2. Each of those into a further 3, because now each of those is pi on 6. Okay, so I'm scaling my axis using units of pi on 6. I'm also going to put 2 pi on 6 back here because I want to be able to think through that left translation to the left by pi on 3. I won't actually draw the graph in back here, but it's helpful to think about where it's going to start in terms of getting your shape right. Okay. The next thing I would say when we're doing a graph with a horizontal translation, the first thing I would do would be to mark in the points without the translation, the 5 key points that define one period of the graph without the translation. Okay, so for the time being, if we forget about the translation to the left by pi on 3, and we just think about plotting out a graph with an amplitude of 3 and a period of 2 pi and a positive sine graph, okay? So if I plot out those points, my graph would start here at 0, the sine graph finishes at the end of the period at 0, halfway along the period, which is pi, it's also at 0. Halfway between those first two x-intercepts, it will have its maximum value in this case because there was no reflection. And in this case, that maximum value was 3, I think, wasn't it? Amplitude was 3, yes. Okay, I'm going to mark that same negative 3 down here. So I'm halfway between the second two intercepts. My graph will have its minimum value, so it'll be at negative 3. Okay, so if I was going to, just let me adjust my pen slightly. So without the translation, this would be this graph here. Okay, so I wouldn't draw it in. I would just think through those 5 points that I've just marked in green. Okay, now what we want to think about is we now want to move this graph to the left by pi on 3. Now on my scale is in units of pi on 6, so that is moving to the left by 2 pi on 6. So that point that was at the origin is going to go back there to negative pi on 3, negative 2 pi on 6. This point up here at the maximum is going to come back here to the left by 2 of these units. Okay. So it's going to come back here and it will correspond with pi on 6 now. This x-intercept is going to come to the left by pi on 3 or 2 pi on 6, so it's going to end up here. This minimum point is again going to come to the left by pi on 3, which is 2 pi on 6, so it's going to correspond with that value there. Alright, and my final x-intercept is going to come to the left by pi on 3 or 2 pi on 6. So now I've got 5 key points that define the period. Okay. Now, the next thing I want to think about is, just let me reduce that pen size for a second, is, okay, if I were to draw one full period, my graph is going to look like this. Okay, however, that's not the domain over which I want to draw this graph. I don't want this bit back here, and I do need a bit more in this region. Okay, so what I want to think about here is, let me just draw that graph in as it should be. So let's just erase this little bit here. Okay, so our graph is going to start somewhere here. We're going to need to calculate that point. That's a y-intercept. Okay. And it travels down here, goes here, and then it's going to keep traveling up here. And what I want us to think about is that, remember, this is still one full period from here to here. One period. 2 pi is the period. And so that means that my graph, if the start and end point is still one full period apart, then it should start and end in the same place. Okay, so they should have the same y value. Okay, now I don't want that to be a complete turning point. The turning point isn't at that value, the turning point's out past here, okay? But it should be heading towards a turning point. I might just make that whole thing a little bit less curved. Still not great. Let's try again. Alright, so the key thing is if I work out the y-intercept, I also immediately have the endpoint. Okay, so I'm going to need to calculate the y-intercept. The x-intercepts and the turning points I can calculate using my scale. There's no calculation. I shouldn't have used calculate. I can determine using the scale. Okay, so the first turning point here, remember our scale is counting up in units of pi on 6. It clearly is at pi on 6, 3. 2 pi on 6, 3 pi on 6. This x-intercept is 4 pi on 6, which simplifies to 2 pi on 3. Okay. The next turning point, that was 4 pi on 6, 5 pi on 6, 6 pi on 6, 7 pi on 6. So this turning point is at 7 pi on 6, negative 3. So this was 7 here. So we've got 8 pi on 6, 9 pi on 6, which corresponds with 3 pi on 2, so I know I'm on track. 10 pi on 6 is that next x-intercept. 10 pi on 6 is the same as 5 pi on 3. And then I'm just going to need to now calculate my y-intercept, which will also give me my endpoint. So let's do that calculation. So our y-intercept is when we let x equal 0. So it's going to be y equals 3 times sine of x plus pi, of 0 plus pi on 3. So it is 3 times sine of pi on 3. So we're going to need to know our exact values. So I'm going to recall my special triangle that involves pi on 3 of 60 degrees. So the half an equilateral triangle, which is what makes that angle there pi on 3. If I choose this side length to be length 2, that makes this 1, and I know from Pythagoras' theorem I can calculate that to be root 3. And so therefore, sine of pi on 3, opposite over hypotenuse, it's going to be root 3 over 2. So we've got 3 times root 3 over 2, which means 3 root 3 on 2. So the y-intercept here is at 0, 3 root 3 over 2. And my end point, which has an x-coordinate of 2 pi, will have the same y-coordinate as my y-intercept because they are a full period apart. Okay, so they have the same y value. And so therefore, there is my graph, in purple, of y equals 3 times sine of x plus pi on 3. Okay, let's draw another one. Sketch the graph of y equals cos of 2 times x minus pi on 4 between negative pi and pi. Okay, let's think everything through. We want to think through our shape. It's a positive cos graph, which means it starts at the top and finishes at the top. Amplitude is unchanged, so amplitude is still going to be 1. Period is changed here. Period, we've got an n value of 2 there. Period is 2 pi on n. So we have a period of pi. And we're translating to the right this time by pi on 4. Okay, so again, we want to think through our scale using these two things here. So if we think through the scale, we need a quarter of the period to get the shape to work, so we're going to need pi on 4 for that. And we're also going to go to the right by pi on 4. So those two things marry together nicely and both indicate that we should use a scale of pi on 4, an x-axis scale of pi on 4. Okay, So we've got a slightly different domain here. We're going from negative pi to pi. The period is pi, so we're going to see two complete cos curves. It might not be two perfectly neat cos curves like this, okay? So instead, it might start here, for example, and then it will finish at the same place because it's going to be 1, 2 full periods. Okay, I'm not saying that's exactly what it's going to look like, but we should still see 2 full periods. They won't necessarily be the traditional cos shape, but 2 full repetitions of whatever the shape is. Okay, so negative pi to pi for the domain, so let's put our y-axis in the middle. Okay, so let's have pi. Let's try and get the same distance over here. Negative pi. Half of that is pi on 2, and half again is pi on 4. Okay, so each of those ticks on the axis represents pi on 4, which is what we decided was a suitable scale. Our amplitude is 1, so our y values are going to go between negative 1 and 1. Now, again, what I want to focus on is plotting out the 5 key points that define the first period. Okay, 1, 2, 3, 4, 5, without the translation. So our graph is a cos graph with a period of pi and an amplitude of 1. So without the translation, it would start at the top here, it would finish at the same height, halfway along the period, it would be at the minimum value, and halfway between those max and mins, we'd have x-intercepts. So those 5 red points define the period without the translation. Now let's think about adding in the translation. So we need to translate this graph to the right by pi on 4, which means this point, every point here, is going to move to the right by pi on 4. Okay, so our graph will be here, 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 and here, and that's the end of the period. So this point out here won't be part of it. Okay, so what we've got, if we join that up, we now should have enough. Now remember, that's a turning point there, so just be careful at making sure it actually turns out of there. We have enough information to be able to now continue to follow the pattern to draw the rest of our cos graph. Okay, so what we're seeing is every pi on 4, we get the next key point of the graph. So if we continue to follow the pattern now, okay, so we're at a maximum value, pi on 4 back from there, we'll be back to the x-intercept. Further pi on 4 back, we'll be at the minimum value. Further pi on 4 along, we'll be back to the x-intercept. Further pi on 4 along, we'll be up to the maximum value. And a further pi on 4 along, we'll be back to the x-intercept. Okay, so we join them all up. Okay, we can get rid of our extra little guidelines that helped us along the way if we want. Okay, and then we should be able to mark in our points. So obviously we've got pi 0 there. That's clearly pi on 2, 0. This is clearly negative pi on 2, 0. This is clearly negative pi 0. Our turning points, so that's going to be pi on 4, 1. This will clearly be 3 pi on 4, negative 1, minus pi on 4, negative 1, and minus 3 pi on 4, positive 1. Okay, and so we've got our graph. Now what I want to highlight with this graph is that we sketched a cos graph, but this actually now looks like a sine graph. And I want to be really clear about the fact that the two shapes aren't actually different. Okay, a parabola and a cubic shape are very different. There's absolutely no way to transform that graph to turn it into that graph through translation, reflection, and dilation. However, a sine curve and a cosine curve, if you translate one across by a certain amount, it becomes the same thing. And so what we have happening here in this particular example is that the translation is sufficient to turn what looked like a cos graph into a sine graph. But I want to be clear about the fact that they're not any different. For example, if we just look at this snapshot from here to here, that's absolutely a cos graph. Okay? Whereas if we look at it as starting from here to here, all of a sudden it looks like a sine graph. I want to be clear that they're not different things, okay? So when we talk about parabolas, quadratic graphs, the graph shape we get is called a parabola. The function is a quadratic, the graph shape is a parabola. Y equals sine of x and y equals cos of x actually produce the same graph shape. That graph shape is called a sinusoidal wave. Okay? This shape, this sinusoidal wave, whether you start it from here and look at it as a cos graph, or whether you start it from here and look at it as a sine graph, it's the same shape that's called a sinusoidal wave. Okay, so I want to be clear about the fact that they're actually not different graphs, but just depending on whether it's written as a sine or a cosine graph will determine how we go about drawing it. Okay, let's have a look at, I think, one further example. So we want to sketch this particular graph here. So again, let's think through and plan out before we draw our graph. So the shape is a negative cos graph. So it's going to start at the bottom and go up. Amplitude is unchanged. It's still 1. The period is changed. It is 2 pi over n, which in this case is a third. 2 pi divided by 1/3 is 2 pi times 3, which is 6 pi. Okay, now the domain of 0 to 6 pi makes sense. We're going to see one complete period. The minus pi on 2 in the bracket means that we're going to move this graph to the right by pi on 2. Okay, again we want to think through scale. Okay, so for the scale, we need a quarter of the period to get the shape right. So we're going to need 3 pi on 2. Okay, so we need to be able to work in units of pi on 2, which is also what we want for the translation to the right. Okay, so our scale is going to need to encompass units of pi on 2, and then we should be able to incorporate both the horizontal translation and getting the shape right, and all our x-intercepts and turning points therefore will be sort of calculated for us by the scale. We shouldn't need to be solving any equations. Okay, let's draw in the graph. So 0 to 6 pi. Okay, so this is 3 pi. Let's divide this into 3 then. So these are now each pi, but we've established we actually need a scale of pi on 2 for this particular graph. So we'll have each of those again. I'll just make the pi unit lines a little larger, just so we can kind of help to follow our scale, be clear where we're at. Okay, so each of those represents pi on 2. Again, let's now plot out one period of the graph without any horizontal translation. So I don't mean plot it out fully, let's just mark the points where they would be. Okay, so without any horizontal translation, it's a negative cosine curve, so we've got thinking about the shape. So let me just mark in my amplitude, so -1 to 1. So it starts at the bottom. Sorry, let me just get a thicker pen. Starts at the bottom, and at the end of the period, which is 6 pi away, it will also finish at the bottom. Now once again, if you want to rule yourself in some rough kind of pencil guidelines, just to help keep your graph straight, that's fine. So, oh sorry, my apologies. At the end of the period, we will be at 6 pi as well. Okay, halfway along the period, we have our maximum value. Between the maximum and minimum is where we will cross the x-axis. Okay, between the max and minimum is where we'll cross the x-axis. Alright, so they would be our 5 points that define the curve without the translation to the right by pi on 2. So what we now want to do, is take this graph and move each of these key points to the right by pi on 2, which is just one tick on this scale. And so what we're now going to have is, let me just get another colour. Our graph shape will start here, cross here, have a maximum here, cross the x-axis here, and the minimum will be out of the domain. So I'm still going to mark that point. It helps to give me a sense of where I'm heading, but I'm going to stop drawing at 6 pi. Alright, so joining them up. Try that again. Alright, now I'm heading towards this point that's outside of the domain, but I'm going to stop in line with 6 pi, okay? And so my graph is going to sort of stop somewhere there. It's not going to be a turning point there. The turning point's happening down here, but it should be starting to curve back in heading towards the turning point. So we should be sort of getting a sense of, you know, slight curve. It was probably better the first time around. Okay, now once again, the distance between our endpoint and our y-axis is a full period. The period is 6 pi. And so therefore, we should be starting and finishing at that same y value if they are one full period apart. Okay, so the y value I've stopped at my endpoint there should be that same y value on my y-axis. And then I want to join things up. Okay, let's mark in what I've got, and then we'll need to calculate our y-intercept and our endpoint. So remembering each tick on my scale represents pi on 2, so this first turning point is at pi on 2, negative 1. 2 pi on 2, 3 pi on 2, 4 pi on 2, or 2 pi for that x-intercept. 5, 6, 7 pi on 2 for the turning point. Continuing to count 8, 9, 10 pi on 2, which is 5 pi for the x-intercept. Then we just need our y-intercept, which will also give us our endpoint. So our y-intercept, we let x equal 0, so we're going to have negative cos of 1/3 times pi on 2. So we have negative cos of pi on 6. Okay, so again, we need to know our exact values. We need to be able to generate them. Okay, again, don't just rely on being able to look up your table in your booklet, because you will not have that in a test or an exam. So half an equilateral triangle, okay, pi on 6 is 30 degrees, so that's the angle up the top here. If we let the equilateral triangle have a side length of 2, that makes that 2, this 1, and Pythagoras can be used to calculate that that's root 3. Now if we want cos of pi on 6, so if this is pi on 6 here, okay, that makes this the adjacent side and this the hypotenuse. And so therefore, cos of pi on 6 is root 3 on 2. So we've got negative cos of pi on 6, so negative root 3 on 2. So our y-intercept is 0, negative root 3 on 2, and our endpoint is 6 pi, negative root 3 on 2. And there we have our completed cos graph. Okay, the work today is from exercise 14I. Once again, I cannot stress enough the importance of planning, thinking clearly about the scale. You should not need to solve any equations to find any x-intercepts or any turning points of these graphs if all you're doing is changing period, amplitude, and translating left or right. Planning the scale will enable you to find what you need to find simply through counting. We'll have a look at in subsequent videos. We're going to take a break from graphs for a little bit in the next few videos and look at solving trig equations, so that then we can begin to translate our graphs up and down where we will need to be able to actually solve an equation to find the x-intercepts. But at this point, we don't need to do it, and we shouldn't. Solving a trig equation is not the most fun thing in the world, and so if we can avoid doing it, we want to avoid doing it, and we can avoid doing that simply by thinking through the scale of our x-axis. Okay, and that involves thinking about the period and the horizontal translation. Okay, so exercise 14I is the work for today's lesson.